This video is going to go through the notes that I would have discussed in class last week when I was sick. And it's on Chapter 9, Reaction Rates and Equilibrium. Alright, the first thing we're going to start talking about is the collision theory. And the collision theory says that reactions occur when we have three things met. We have to have sufficient number of collisions, so the more collisions that are possible, the better the reaction would occur. The collisions have sufficient energy to break the bonds, because they're going to have to break bonds in order to form new ones. So they have to hit together hard enough that it's going to break those bonds. And thirdly, the molecules collide with the right orientation. Meaning, if we're going to have an N and an O get together, they have to be correct. They have to be hitting with the correct orientation. And the bottom line, the more collisions that we have, the faster the reaction is going to occur. So when we look at speeds of reactions, especially in our lab next week, we're going to be talking about this collision theory. And you're going to be asked to explain why those reactions go faster in terms of the collision theory. Alright, so the activation energy is the minimum energy that's needed for the reaction to occur. So if this is where my reactants are, and this is where my products are, the activation energy is the energy that I have to overcome in order for that reaction to occur. And that's the difference between the reactants and then this activated complex up here. So the activation energy is the energy that I have to add. Once I overcome the activation energy, then the reaction will proceed. Now, when we talk about reaction rate, that's how fast a reaction occurs. And that's going to be affected by things like temperature, concentration, and the addition of a catalyst. And in our lab, we're going to look at all three of those things affecting the rate. If we have a higher temperature, that means that the particles are going to move faster, meaning they have more kinetic energy. And if they move faster, there's going to be more collisions occurring, and those collisions are going to have more energy since the particles are moving faster. So because they not only cause more collisions and more energy in those collisions, that means it's going to happen faster. So for example, most of the time when we have foods that are going to expire, or if things that could get old, we put them in the refrigerator because that's going to lower the temperature, and if they lower the temperature, the reaction rate should go slower. So in our lab, one of the things that we'll be doing is taking it at different temperatures and seeing how long it takes the reaction to occur. The next thing is concentration. So if we have more concentration of reactants, meaning more molecules in there, that means there's a possibility for more collisions. And if we have more collisions, according to the collision theory, that's going to increase the rate of our reaction. And the other thing that we're going to do in our lab is change the concentration and see if that affects the rate of the reaction. Lastly, a catalyst speeds up the rate of the reaction, and it does this by lowering the activation energy. So that hill that we talked about earlier, if this is where the activation energy was, adding a catalyst will lower the activation energy, and that's going to be able to make the reaction go faster because it doesn't have to overcome as much energy first to begin with. And we're also going to look at the addition of a catalyst in our lab. Now we look at reversible reactions. Those are reactions that can happen both ways. They can go both forward and reverse. And when we look at those in a chemical reaction, they're going to have a double arrow. So instead of just a yield sign, they're going to have a double arrow, meaning it can go forward and it can go reverse. Not every reaction is reversible, but those that are have this double arrow. Now at equilibrium, what happens is that the rate of the forward and the rate of the reverse are the same. Now that doesn't mean that they have the same concentrations. That just means that there's not going to be any more change in the concentration, because the amount that's going from forward, meaning breaking down of the reactants to form products, and the products breaking down to form reactants are the same. So that just means that it's going to stay the same. So whatever you had for your concentrations will stay the same. That doesn't mean that both sides are the same, but that just means that the rates of the forward and the reverse are the same, and that's what we call equilibrium. So here's an example of a reversible reaction. Those are the ones that we have to look at for equilibrium, because we can't have a forward and a reverse rate unless it's a reversible reaction. So at equilibrium, the concentrations of the reactants and the products are constant, meaning the reactants, if I measure now and later, it'll be the same. And then if I measure the products now and later, their concentration will be the same. But not necessarily the reactants and products have the same concentration. And the reaction is going to continue with the rate of the forward and the reverse being the same. So if we have a reaction, and here we're having just A going to B, little a and little b are the coefficients, then we can write an equilibrium expression. And the equilibrium expression is called Kc. That represents the equilibrium constant. We're going to put products over reactants. So my products in this reaction are B, and this little bracket means concentration, like molarity, and then I would put A on the bottom, so products over reactants. Then the little a and the little b are the coefficients, so those become the superscripts. So if this were my reaction, in order to write the equilibrium expression, I would say that my constant, and this little c down here stands for concentration, so I would take my products, water, and water is a liquid, and then I have chlorine, which is a gas, I have oxygen, which is a gas, and then I have HCl, which is a gas. Now in our equilibrium expression, we only put in gases and aqueous, so liquids will not show up in there. Water doesn't show up in here, and that's because water is a liquid. So my other product would be Cl2, its concentration squared because it has a coefficient of 2. My reactants are going to be oxygen, so here's oxygen, and then HCl, and it's going to be to the 4th power because it has a coefficient of 4. Now, if we have a homogeneous equilibrium, that means all of the phases are the same. So like they would all be gases or all be aqueous. The one that we had before was a heterogeneous because I had some things that were liquids and some that were gases. So in that case, they have different states. And the concentrations of solids and liquids don't show up in my equilibrium expression, only gases or aqueous. So if this were my equilibrium expression, if this were my equation to write the equilibrium expression, I would put products over the reactants, but the solids aren't shown in there. So I would only have CO2, and it does not have any superscript because it has a coefficient of 1, and then I would have water. And these are multiplied together. Alright, so I have an example here where we're going to calculate. So in this case, they give me my equation, and then they're giving me values for H2, I2, and HI. So the first thing I'm going to do is write my expression, where I do my products over my reactants. So it would be HI squared, because it has a coefficient of 2. I would put that over H2 times I2. I'm going to put in my value that I had for HI, which it told me was 1.47. So I put in 1.47 and it becomes squared. Then I'm going to put in my H2 value, which was 0.2. And I'm also going to put in my I2 value, which was also 0.2. So 0.2 times 0.2. So 1.47 squared divided by 0.2 times 0.2. And I get a value of 54. And we'll be talking more about what those equilibrium constants mean. But for right now, we should be able to take a reaction, write the equilibrium constant by putting the products over the reactants, and then doing some calculations with those where I would simply plug in the concentrations of those products and reactants in order to find my equilibrium constant. I could also be given the value of my equilibrium constant and maybe two things and be asked to find another one. But the goal is always to take the expression, or the equation, write the expression, and then substitute the numbers in and solve for the piece that you don't have. So those are going to be some practice calculations that we'll see for equilibrium constants. And there will be more of those calculations. They are shown in a video where it has practice problems from chapter 9 that you could take a look at.